All right, now let's talk about the properties of a t-interval. Now, we use a t-interval because we do not know the population standard deviation. So when we were using our intervals for proportions, we could calculate this interval using the standard error or the claim based on the true value of p. Well, here, like we said earlier, we're estimating two parameters now. We're estimating mu and sigma. So the main reason we use a t-interval is simply because we do not know the value of the population standard deviation, so we're accounting for this extra variation. Now, if you did know sigma, we would calculate a z-interval. Not a z-interval for a proportion, but a z-interval for a mean. Now, that goes beyond the scope of this course, so we're not going to worry about that. So in this example here, we're going to just use our x bar and s to estimate mu and sigma. Because again, most oftentimes we do not know the value of the population mean or the population standard deviation. So I'm going to show you how I calculate this here. Well, the financial aid office wishes to estimate the cost of textbooks per quarter for students at Milton University. The financial aid office is pretty sure that the amount of money spent on books by all students varies widely, and that a reasonable amount for mu is 550 and for sigma is 150. And we're going to treat that as x bar and s. Now, a random sample of 1,000 students are surveyed. So assuming the conditions are met, which they are, we're going to determine a 90% and a 95% confidence interval. So if I open up my calculator here and I go to calculate, I'm going to go here to menu, statistics. I want a confidence interval. Well, we're going to use a t-interval. Now, we're not going to worry too much about the data. I'll show you some in-class examples of this. What we're going to look at is the stats. So in our stats, we had a mean of 550 and a standard deviation of 150. And a sample size of 1,000. And we want 90% confidence. So we're going to use 0.9 here. So now I have everything that I need. And no, I don't want that. I want 0.9. And let's click OK. And my confidence interval is between 542 and 557, which is what I have written right here. Now the width of this interval is about 15.62. So let's suppose that we up the confidence level. So let's go ahead here and we're going to do the same thing. Menus, statistics, confidence intervals, a t-interval. Again, we're going to use the stats and 550, 150, 1,000, and look, it's always set to 95% confidence. Well, now my interval is from 540 to 559, which gives me a wider interval of about 18.62. So like with our z intervals, when we increase the confidence level, we increase the width of the interval. Now, let's suppose that we use 2,000 students, so I'm going to use the same 550, 150, 90%, but now n is 2,000, and I would get this width of an interval between 544 and 552. And if I, again, up the confidence and change the sample size, then we get the following. So let me compare 4 to 1. So in interval 4 here, when I use a larger sample size, my width decreases. Same here in interval 5, when I use a larger sample size despite the same confidence level, my width also decreased. So what happens? Well, whenever I increase the sample size, the width of the interval decreases. And that's because this is dealing with the margin of error. So that gives us some properties of confidence intervals for mu. The higher the confidence level, the wider the interval. The larger the sample size, the smaller the interval, right? Because larger samples tend to have less variability. When we are using higher confidence, we are running a little bit more risk, so we're just casting our net a little bit further. And this is all based on the relationships here that we see in the margin of error. So as the confidence level changes, so t star, and the sample size changes n, this is what happens here. Now I put a star here because if we have a larger standard deviation, then yes, the margin of error will be larger, and that'll give us a wider interval. But think about this. If I'm looking at my same sample, there's no way for me to change that same sample standard deviation. I would have to take a completely different random sample to get a larger standard deviation. So I put a star by this because mathematically, while it is true, it's not true in practical purposes, right? When we're looking at it from the statistical standpoint. So really the two important ones are that as we increase the confidence level, the wider the interval gets, and the larger the sample size, the smaller the interval gets because of the relationship with the margin of error. Well, very similar to our proportions, the margin of error is the critical value times the standard error, and it basically tells us how far away our estimate of x bar is from the actual value. Because remember, we're trying to use x bar to estimate mu. So to do this, we run into an error because typically t star, the critical value, depends on the degrees of freedom. But if I'm looking for the sample size, I won't know what the degrees of freedom is because I need the sample size. Similarly, since t star depends on that, I will have to also use a z star. And again, t star closely approximates z star and s closely approximates the standard deviation, which is what I did right here. So t to z, s to sigma. So what we'll do is when we calculate our margin of error, and I showed you here the first manipulation, is I did t times the standard deviation over sigma. I will move n to the other side. I'll divide by e, and then to get rid of this square root here, I'll just square both sides. Well, then what I'm going to do is I'm going to substitute in what I believe to be true, that t closely approximates z, and that s closely approximates sigma. So very similar to our formula that we learned in Unit 6, we have this formula here to give me the sample size. So if I want my estimate to be useful, as in from the first example, I want it to be within $20 of the true population mean. How large of a sample should be used if I want to use 95% confidence? Well, again, if I'm using z for 95% confidence, we can just check our formula sheet. If I'm using 95% confidence for a z, the standard normal, I'm going to use a critical value of 1.96. My margin of error here is 20, and the sigma was stated in the original problem as 150. So when I do these calculations, I get a sample of 216.09, and larger samples have less variability, so again, we want a smaller margin of error. So I'm going to round up. So I would need 217 students in order to accomplish this goal. All right, so what I want you to do now is go ahead and pause the video and go ahead and try out the next two example problems. We will come back together and review those and just clarify any underlying questions. Okay, so hopefully not too complicated. Again, it's all about textual evidence. Again, we are assuming we know what sigma is, got our margin of error, and then we're just using our critical values provided to us from our table here. So 90% confidence, 95% confidence, and 99% confidence. These are the more common values, so if you ever forget them, don't worry, they're here at the bottom of your table B values. So we should get a sample size of about 14 students in the first example and a sample of 180 females in the second example. Now, I'll be honest in that finding the sample sizes are a little bit more common for proportions than they are for means, but you still have to be well-versed in doing both because on the AP exam, we're not entirely sure which variation you're going to get. And you will most definitely see both proportions and means on the AP exam, so you need to be ready to navigate between both. Now notice here that I'm often seeing sample mean, I'm seeing sample average, I'm seeing values that are greater than 1. That's usually indicative to me that it is a means problem, a quantitative data, as opposed to categorical data. But that is going to wrap up our study on t-intervals. And in the next lesson, we are going to talk about the one sample t-test for a population mean. And it's going to be very similar to what we've done so far in Unit 6. So stay tuned to learn a little bit more about hypothesis testing.